Hi everyone, I am Mohammad Tamim Musa and today I will be talking about computer networking. We will go step by step through the basics, models, devices and practical setups. Let's keep it simple and interactive. And by the end, you will have a solid idea of how networks really work. So let's get started. Fundamentals of networking. Introduction to networking and its evolution. Let's begin with the fundamentals of networking. So what exactly is a network? A network is simply a collection of devices, also known as nodes, uh, that are connected together to share data, resources, and services. Think of your home Wi-Fi, your phone, and smart TV all part of a small network. Networking has evolved a lot over time. In the early days, it was just two computers connected with a cable. Later, we saw the development of local area network, then the growth of the internet and how advanced technologies like cloud computing and IoT dominate the field. Types of networks. There are different types of networks based on size and purpose. The main four types of networks are LAN, WAN, MAN, and PAN. LAN means local area network, usually within a building or campus. WAN means wide area network, such as internet spanning cities and countries. Okay. MAN, metropolitan area network, which connects across a city. PAN, personal area network, such as Bluetooth connection around a single user. Okay, let's go to the next topic, nodes and media. In a network, each device is called a node. Computers, printers, routers, even IoT devices like smart bulbs. To connect nodes, we use media. Optical fiber. We use optical fiber for high-speed long-distance data. Wi-Fi for wireless connections inside buildings. Bluetooth for short-range personal connections. Without proper media, communication between nodes would not be possible. Components of a network. Every network has certain building blocks. Sender, devices that create the message. Receiver, devices that gets the message. Data, the message itself. Medium, the channel could be cable or wireless. Protocol, rules that both sides must follow. Think of protocols like languages. If I speak in Bangla and you only understand Canadian language, we can't communicate. Okay. Computers face the same challenge. For example, HTTP is the protocol you browse uses when opening a website. FTP is used for file transfer. So without protocols, networks would be total chaos. The third topic is classification of networks. Networks can be classified in two main ways. The number one is by ownership, the number two is by geographical area. By ownership, public networks like the internet open for all. Private networks like your office LAN controlled by one organization. Okay. By geographical area, PAN, LAN, MAN, and WAN. The definition helps us choose the right type of network for the right job. Uses of networks. Why do we even need networks? Okay. Here are some common uses that we need networks. Data sharing, email, cloud, storage, social media, hardware sharing. Multiple people use the same printer. Software sharing, Office 365 or Google Documents across accessed online that called software sharing, remote access, working from home but logging into your office server, it means remote access. So networks save cost, time and make collaboration possible. Networking opportunities in Bangladesh. Networking is not just theory, it's also a career path in Bangladesh and worldwide. Companies need network engineers who design and manage networks, cloud administrators who handle uh, AWS, Azure, Google Cloud, IoT specialists who work on smart devices, cybersecurity analysts who defend networks from hackers. Classification like CCNA, Compose TIA Network Plus, Azure Cloud and grade entry points, so networking is full of opportunities. Module 2, Network Models. Now that we have covered the basics of networking, let's dive into how data actually flows between devices. To understand that, we use network models. These models act like blueprints, breaking down complex communication into simpler layers. There are two main models we look at: the OSI model, ideal for learning, the TCP/IP model, what we can use in real life. Let's start with OSI. OSI model. The OSI model stands for Open System Interconnection. It's a 7-layer framework created by the ISO International Standards Organization to help us understand how data travels from one device to another. Think of it like sending a parcel through a postal system. The message has to go through multiple steps, each handling the specific task. The 7 layers of OSI. Physical layer deals with the actual medium cables, connectors, signals. Example: Ethernet cables, voltage, labels, fiber optics. Think of roads where cars travel. Link layer organize data into frames, handle MAC addresses and error detection. Devices: switches, NICs, analogy like traffic lights and street signs on the road. Network layer handles routing, IP addresses and packet forwarding. Devices, routers, protocols, IP, ICMP like Google Maps choosing the best route. Transport layer ensures reliable delivery with TCP or fast delivery with UDP. Application layer messages and maintains sessions between applications. Keeps track of ongoing communication like Zoom call sessions. Presentation layer translates and formats data, compression, character encoding. Example: SSL, TLS. Application layer where the users interact with browsers, emails, clients, apps. Application layer where the users interacts with browsers, email clients, apps. Protocols: HTTP, FTP, SMTP. The next topic is TCP or IP model. The TCP model is what we actually use today. It has 4 layers. Number 1, application, HTTP, SMTP, FTP are examples. Number 2 is transport, TCP, UDP. Internet is IP addressing. Network access is physical plus data link. So while OSI is great for learning, TCP/IP is used in practice. Now, Module 3, Network Media, Cabling and Topology. Let's start with network media. The physical path data travels through. Without media, networking would not exist. There are two main types of network media. Wired media, twisted pair cable, most common used in LANs, UTP, unshielded twisted pair, and STP, shielded twisted pair. Speeds up to 10 gigabytes, maybe Gbps, depending on category. Coaxial cable used in old LANs and still in cable TV. Fiber optic cable uses light on electricity, supports very high speeds over long distance. Expensive used in backbone networks and ISPs. The number 2 is wireless media. Wi-Fi, most common wireless LAN tech, microwave and satellite, used in remote areas or maybe global links, Bluetooth, for short-range personal devices like earbuds or smartwatches. Cabling. Let's look deeper into the practical side of cabling. Ethernet cables. RJ45 connector. RJ45 connector is standard connector for Ethernet. T56HF versus T568B. Writing standards. A and V only differ in wire color order. As long as both ends match with the cable will work. Crossover cables use A on one and V on the other. Used for direct PC to PC connection in the past. Tools we needed. Crimping tool to attach RJ45 heads. Cable tester to verify if cable is working. Wire stripper and cutter for net preparation. Now our last topic of Module 3 is topology. Now let's talk about network topology. Topology simply means the arrangement of devices in a network, how they are physically or logically connected. You can think of it like a city road map. The way houses, offices, and markets are connected by roads is similar to how computers, printers, and servers are connected by cables and switches. Let's go through the main types one by one. Okay. At first, bus topology. In a bus topology, all devices are connected to a single main cable called the bus. In a bus topology, all devices are connected like a bus. Imagine one straight main road in a small town, and every shop or houses is directly connected to the road. It is cheap and simple to set up, which made it popular in the early days of networking. But here is the problem: if that on road is blocked, no one can move. If the bus cable fails, the entire network goes down. Also, because everyone is sharing the same road, traffic jams are, in network terms, data collisions can happen when many people try to send data at the same time. That's why bus topology is rarely used today. Star topology. Now let's move to star topology, which is the most common today in this layout. Every device is connected to a central device like a switch or hub. Think of it as a round boat in a city where all the houses have their own private road leading directly to the center. The advantage is clear. If one house's road is blocked, the others are unaffected. In the same way, if one computer falls, the rest of the network continues working. It is also much easier to troubleshoot since everywhere goes through the central hub. But here is the catch. If the round board itself gets blocked, the entire traffic stops similarly. If the central switch falls, the whole network goes down. Example, almost every modern office or school network uses star topology. Now, ring topology. In a ring topology, devices are connected in a circle. Each device passes data to the next unit it reaches the right destination. It is like a circle metro line where each station is connected to the next. The benefit is that it avoids data collisions since data moves in one direction. However, the weakness is clear. If one station is closed, the whole circle can break down. To solve this, sometimes networks use rings for backup. Example, older version of IBM Check-in ring networks use the topology, and in some industrial control system ring is still used. Mesh topology. Mesh topology is where every device is connected to many others. Imagine a city where every building has roads directly to several other buildings. This means if one road is blocked, traffic can simply take another road. The main advantage is high reliability. Even if multiple connections fail, the network will still work because of the multiple roads. That's why mesh is often used in uh, critical systems like the military aircraft system or even modern Wi-Fi mesh routers that people use at home to cover large areas. The downside is cost and complexity. So many cables and ports are required to set up this network. It becomes expensive for large networks. The last one is hybrid topology. Finally, most real world networks use hybrid topology, a mix of two or more types, just like a city combines highways might combine star and bus or star and ring. For example, is an office building, each floor might use star topology and then all floors are connected together using bus or ring. Hybrid topology gives flexibility because it lets engineer choose the best decision for different parts of the network. So topology is like the roadmap of your network. Bus equal one main road, star equal round boat with all roads connected to the center. Ring, circular metro line, mesh, every building connected to many others. Hybrid, a mix like real city road systems. A good topology ensures smooth data flow, easy maintenance, and strong reliability. When network engineers design a system, they carefully balance cost, performance, and reliability, before choosing which topology to use. In short, topology is not just about shapes like lines, stars, or circles. It can about building a network that people can depend on. just like well-planned city roadmap. Module 4: NIC network devices and software. Our first topic is NIC and MAC address. Every device needs a network inference card. NIC to connect could be wired, wireless, or virtual. Each NIC has a MAC address, a unique hardware ID like a fingerprint for devices. Okay. Our second topic is network devices. Key devices include repeater, hub, switch, router, gateway, bridge, or ONU. Okay. Repeater boost weak signals. Hub connects devices but sends data to all. Switch smarter, sends data only on the right device. Router connects different networks. Gateway or ONU support communication between different technologies. Routers and switches are the backbone of modern network. Networking software. Hardware isn't enough, we need software. Wireshark, packet tracer, PRTG, IP calculators. These tools make network management possible. Wireshark means packet analysis. Packet tracer means simulation. PRTG means monitoring. IP calculators means subnet planning. Module 5: Protocols, IP addressing, and subnetting. Their first topic is protocols. Protocols means rules. IP, TCP, UDP, SMTP, FTP. Okay, IP means addressing. TCP means reliable delivery. UDP means fast but no guarantee. SMTP means email. FTP means file transfer. Second topic is IP addressing. Devices need IP addresses. IPv4 32-bit looks like 192.168.1.1. IPv6 means IP version 6, 120 has a 128-bit, much bigger, looks like 2001. DBH1. Public versus private IPS classes ABC used in networking. Third topic is subnetting. To use IPS efficiently, we divide into subnets. Two methods: FLSM fixed size, BLSM variable size. Subnetting reduces wastage and improves security. Module 6: Office network setup. Equipment and data collection. Devices: PCs, printers, phones, cameras. Services: email, volume IP, file sharing, internet. Bandwidth based on uses. Security: VPN, firewalls, antivirus. Growth: plan for expansion. Essential equipment: router, switches, structured cabling, firewall, UTM, patch. The next topic is design. Physical layout: floor plan, switch, web placement. Logical design: IP plan, VLANs per department. DHCP, scopers, inter VLAN routing. Security architecture: DMG for public servers, firewall rules between VLANs, isolate guest Wi-Fi. Tools: The third topic of Module 6 is cabling and router configuration. Cabling. Use T568V label both ends. Test cables. Router setup. 1. When static DHCP IPNet firewall LAN set subnets DHCP whose wireless WPA3 VLAN embedded SSIDs verification and maintenance testing tools ping and tracer route for connectivity IP configuration to verify IP settings. Use Wireshark for packet capture. Nmap to scan devices and test open ports. NetFlow SNMP for traffic monitoring. Ongoing maintenance tasks. Backup configurations regularly. Update firmware software for routers, switches, and firewalls. Module 7. Packet Tracer is a powerful tool for simulating networks. Simulate routers, switches, PCS, and servers. Configure VLANs, static, dynamic routing, DHCP, DNS, and NET. Visualize packet flow using simulation mode. Practice exam like scenarios for CCNA use cases or test office setups before deployment. Learn CLI commands in a safe environment. The next topic is DHCP. DHCP configuration. DORA process. Discover client sends broadcast to find DHCP server. Server offers an IP address. Client asks to expect the offer. Acknowledge. Server confirms list. Packet tracer demo. Assign DHCP to a router or server. Define IP pool, default gateway, DNS. Watch the packet interaction in simulation mode. NET types. NET allows multiple private IPs to use a single public IP. Types recap. Static NET 1.1 mapping used for servers accessible from internet. Dynamic NET uses a pool of public IPs. PAT port address translation, also called NAT overload. Multiple private devices share one public IP using different port numbers. Why NAT matters? Saves public IPs, adds a basic layer of security, makes internal addressing flexible. Our next topic is NAT configuration. Packet tracer static NAT setup. Assign private IP to internal server in 192.168.1.10. Set interface as IPNet inside and WAN as IPNet outside. Create static NAT rule. IPNet inside source static 192.168.1.10 1.10.203.0.113.5. Test using simulation mode or PC ping. Use case: host a web server or mail server that external users must access. PAT configuration. PAT setup example. Access list 1 permit 192.168.1.0 0.0.0.255. IPNet inside source list 1 inference fast Ethernet 0x0 overload. Steps: define internal IPs in an ACL. Assign inside and outside inference, enable net overload. Testing use multiple PCS to access a simulate website or ping an external server. Combine DHCP plus PAT for a fully automated network. Alright everyone, we have reached the end of our session. Thank you all for staying with me.